BCE Chemistry, Key Skills for Unit 3 and 4, Calculating Units. Well, for students who just started or are about to start Unit 3-4, you might not yet have heard about this skill being specifically taught, unlike other skills such as TOEIC. Okay. However, after taking hundreds of students through the course, I think calculating units is a skill rather intrinsic to all studies of sciences, even if you are doing physics or even biology. If you're in year 12 now, you probably have done it many times in your calculation, without realizing that you're calculating units in addition to the numbers. Now, the basic idea is that units can be calculated, just like numbers. Therefore, it is an indication to whether our calculation is correct. We can use it to check our answers. Units can also guide us in unfamiliar situations where we might not necessarily know the exact formula for calculations. Now, let's have a look at the mathematics behind calculating units. So when we were learning about fractions, we were told that when 1 is divided by a fraction, numerator over denominator, then we basically get the reciprocal of that particular fraction that was divided by, right? The denominator and numerator will swap place. So ideally, the following equation here, this is written in symbolic terms, okay? So numerator divided by numerator over denominator equals to, well, multiply the numerator multiplied by the reciprocal of that fraction, and therefore we end up, because these cancels out, we end up with denominator by itself. So in this way, whenever we're unsure about something, we can refer to units to do your calculations. A more relevant example, so compound units, for example, kilojoules per mole, kilojoules per gram, density and/or concentration, although completely different meanings, but sometimes they have the same units, compound unit, grams over mils, right? They are just like fractions that can be calculated. I'm sure you're very familiar with them from thermochemistry calculations, right? So kilojoules divided by kilojoules per mole, well, our kilojoules per mole is this one, right? It's basically moles. You can see that compound units are just like fractions. We can operate with them just like how we operate with fractions, right? So for example, let's say if this is a density unit, and when we want to get mass from our density unit, we don't have to wonder about, am I going to divide or divide by or multiply, which one's which one. We just have to look at it as a fraction, okay? If we want to obtain mass from density, we have to multiply by the volume, because we want to cancel out this volume here to get mass, right? Grams is the unit for mass, okay? So when we don't know the exact formula, look for clues in the units. Now, this example is from 2017 VCA exam. Okay, so I really think it's a really good example to show us that how we could know the least amount of chemistry, but using our knowledge of units, we could still eventually get the answer. Okay, so initially, this question gave us a bit of context. We are basically comparing the fields, but the details of the context are not very relevant to the calculation we want to explore here. So we're going to skip to the table. So on table, we know that the fuels we're comparing is petrodiesel versus biodiesel. We have the major component, but remember that both petrol and biodiesels are mixtures. So we can't really rely upon the major component here to perform some energy calculations using the formula, because they're mixtures eventually. But the good thing is the question did give us the energy content measured in mJ per kilograms of each of the fuels. So basically, if we know the mass, we can just use these numbers to find energy. Or if we use energy, we could go the other way to find out about mass. Just use these two numbers, right? And CO2 emissions, well, we'll see when that will come to be useful. Okay, so The question says, assume that combustion occurs in an unlimited supply of oxygen for um, each of the calculations, which means it is a complete combustion. We can safely use these energy content values. We need to calculate the number of liters. Oh, that doesn't sound good because we don't have any liters on this table. Liters of biodiesel that are required to be burned to produce the same amount of energy as 2.5 kilograms of petrodiesel, and density. Okay, so look at that. In order to get liters, the only way is through density, because only density brings in the unit of liters. But many of us might have already forgotten that density formula from year 9 science. But don't worry, the units will guide us anyways, okay? So we understand to get that unit, we just need to use a kilogram to divide kilograms per liter. How do I know it's divide, not multiply? Because I know I want liters at the end. And dividing a compound unit like this is like multiplying its reciprocal, where I can cancel out the kilograms in my calculation and get liters eventually. So we know that in order to obtain the liters of biodiesel, we need to get the liters of the mass of biodiesel that are required. But the mass of biodiesel is tied to the amount of energy that is required to produce, right? So what is the energy that needed to be produced? It's the same amount of energy as 2.5 kilograms of petrodiesel. I think right now you more or less have an idea what we need to do, right? We have the energy content of petrodiesel here, which is 43 mJ per kilograms, okay? If we could get rid of these kilograms, we can get the energy that eventually will lead to the mass that will eventually lead to liters, okay? So the energy that are required is 43 megajoules per kilograms for petrodiesel, multiplied by the amount of petrodiesels in mass, and in that we will actually get the number 107.5 mj. I'm sorry, kilograms. And you can see that as we were doing the calculations, if we do include units in our writing of these calculations, you eventually see units and units are doing the calculation as well, just like numbers, right? When 43 is multiplied by 2.5, mj per kilogram is also multiplying kg, and we cancel off kg, and therefore we end up with mj, right? So units are also going through calculation, not essentially the formula will give us an idea, will give us a solid conclusion. This is the way that we get energy, which is using energy content to multiply the mass of that fuel. But you see, units also says that, so we know that's correct, right? Now we have mj. We want to go from mj to kg. mj to kg. We eventually need some kind of bridge here, and that bridge is energy content, because that's a compound unit with both mj and kg. And we know that we want to use mj to go to kg. It somehow will be a mj over kg, that kind of calculation, right? Only that will end up with an kg. So this is our thinking, okay? In your mind, we're thinking about this. So what do? We want the mass for biodiesel, and that's the energy the biodiesel is going to produce. So all we need to do is to use the energy that it needs to produce, 0.5 mj, divided by the energy content for that biodiesel, which is mj per kg, and eventually we will end up with 2.82828. The reason I'm keeping so many decimals here is because I don't want to screw up. I don't want to round in the middle of the calculation, so that I can get the most accurate number, right? So, and you can see that that division will actually give us kg as a unit. Okay, so again, we feel like if unit agrees, we agree, and that's correct. Okay, so so now we have kg. We know that the next step is very simply we need to use m to divide by density. Okay, we don't know the exact formula. There's no such formulas from your data book, but based on the units, we know that it must be a division. Okay, so 2.8289 on your calculator. Please save the last number. So at the end, we will eventually arrive at 3.178 liters, right? And for significant figures' sake, we will keep it to 3.2 liters, okay? Because 38 and 43, they're only 2 sig figs, and the density is also 2 sig figs, so we keep it to 2 significant figures at the end, right? Okay. Now, the second part of this question is even more interesting, okay? So okay, so this 1 mark question may stun many students because look, calculate the mass of carbon dioxide that would be produced from 3.91 kilograms of biodiesel, from combustion of this much of biodiesel, right? Okay, so well, we have never really learned about any formula to calculate CO2 from combustion of a particular fuel. Even the universal gas equation that has something to do with gas has nothing to do with what it is asking, okay? Well, again, units come to the rescue. Have a look at the last column here. The title states CO2 emission and kilograms CO2 over kilograms of fuel. Okay, so if you have put kilograms of fuel as the denominator to get the mass of carbon dioxide, we just need to really find the kilograms of that fuel. We have never used any unit or learned any unit, but we just take it as it is, right? So, okay, since you say for biodiesel, 2.52 kilograms of CO2 would be produced if you have burned 1 kilograms of fuel, okay? Whenever you see something on the denominator, you can just assume that it's 1, right? The number in front of it is 1. 1 kilograms of biodiesel will produce 2.52 kilograms of CO2. Now, what's the mass of CO2 if I have burned not 1, but 3.91 kilograms? Haha, this is our thinking, right? So to write the answer, eventually, the mass of CO2 that will be produced is 3.91 multiplied by 2.51. The unit is way too long. I'm not going to write it here. I'm going to save it. So in the end, we will get our answer to be 9.81 kg. Okay, 9.8 kg.